Good morning, a very good morning to all of you. Uh, I hope you are all keeping well and and having a good time. So, without much delay, uh, I would like to first welcome you all to this hands-on webinar on design of composite beams. I hope my name is Arnav Anuj Kasar, and I hope all of you have taken the printouts of the handout material that I have shared with you in the morning. So we will first move towards a small video of Jaypee University introducing the university to all of you. So please have a look at our wonderful university.
Experience tranquility as you drive through the population-free lush green slopes of Waknaghat to reach functionality and aesthetically spread 25 acres of easy-flowing and community-friendly landscape. Welcome to Jaypee University of Information Technology, Waknaghat. Set up in 2002 under the Extraordinary Gazette Notification of Government of Himachal Pradesh. This is the only private university in the state whose chancellor is the governor of Himachal Pradesh. With 108 professors, most of whom are PhD from reputed universities around the world, JUIT offers BTech, MTech, MSc, PhD in computer science, IT electronics and communication engineering, bioinformatics, biotechnology, and civil engineering, whose curriculum is supplemented by SWAYAM and PTEL. A home to almost 2,000 students, this university is twice accredited by NAAC. The world-class state-of-the-art infrastructure of JUIT has 57 labs, including Virtual Lab, eYentra Lab, IoT, lecture theaters, classrooms, tutorial rooms, laboratories, vast auditorium, administrative and faculty offices, an enormous library, and 6 well-equipped gyms. The campus is designed with a vision of creating a university of international repute and highest global standards. Fully equipped with learning tools and web-based educational environment, the campus is planned for the advanced computing infrastructure. Facilities like bank, temple, and helipad are all within the campus. JUIT takes pride in being a member to IEEE Chapter and Computer Society of India Chapter. It also conducts student exchange programs with the University of Nebraska, Omaha, and University of Florida, USA. To give an experience of the real corporate world and understand the challenges that lies ahead, our students also get an opportunity to connect with industry professionals and self-made entrepreneur. Our exclusive placement cell has an excellent placement record. All this has brought us several accolades. We're ranked among the top 100 engineering institutes by NIRF, MHRD. We've been declared Best Private University of Himachal Pradesh by Dialogue India in 2018 for academics and infrastructure. We're also ranked first under category of value for money and third under the category of top private university in 2018 for offering value for money education by India Today. With a hygienic mess named Annapurna, well-furnished hostels with single and double rooms, mechanized laundry, 24/7 water supply, complete power backup, and Wi-Fi connectivity, we ensure that students feel at home while they're away from home. The overall growth in personality and confidence is taken care by conduct of debates, declamation contests, and a host of indoor and outdoor games. NCC Wing for Girls, and a vibrant youth club that organizes popular sports festival called Padakram, literally festival and cultural festival, which further heightens their energy levels. They're also encouraged to develop independence in thought and action, as well as trained to deploy appropriate technology paradigms for given tasks. explore new horizons, and lead teams to solve complex problems. With our learner-centric educational process, students are free to find their own paths and learn their way to limitless opportunities that awaits them. So be a part of Jaypee University of Information Technology, Waknaghat, Himachal Pradesh to be the leaders in innovation, entrepreneurship, creativity, and management. Because this is where we engineer lifelong learners.
Welcome back. Once again, on behalf of Center for Disaster Mitigation, Center for Excellence in Structural Engineering and Disaster Management, I welcome you all to this webinar. Without any delay, I would now request the coordinator of the Center for Structural Engineering and Disaster Management and the head of the Department of Civil Engineering at JUIT Waknaghat, Professor Ashish Kumar, to please introduce our instructor for today and kick start today's webinar. Sir.
Thanks, Arnav. Good morning to all of you. On behalf of Department of Civil Engineering, I welcome you all in this one-day workshop on hands-on design of composite beams, and which is organized today by Center of Excellence in Structural Engineering and Disaster Management. So you have gone through the video of Jaypee University. So that campus is basically spread over a 25 acres of lush green slopes of Waknaghat Hills in Solan, Himachal Pradesh. And this JUIT basically conceived by a joint vision of Government of Himachal Pradesh and our founder chairman of Jaypee Group, Shri Jayprakash Gaurji in 2000. And then university start functioning with student intake in BTech in various branches in 2002. And in 2003, we started our Department of Civil Engineering. So, and the Center of Excellence, this Center of Excellence came into existence in year 2018 with the vision of creating awareness and disseminating the intellectual resources related to the advancement in the structural engineering and the disaster management. So with this vision, in the past 3 years, we have conducted so many workshops on the structural engineering, concrete technology, and disaster management, and we are continue to this commitment of the center. And in this center, we are having the 7 members from different disciplines, from IT, from computer science, and from electronics also. And specifically for this webinar session, I am thankful to our keynote speaker of this session, Dr. Pankaj Kumar. He is assistant professor in Department of Civil Engineering, NIT Nagaland. And let me tell briefly about Dr. Pankaj Kumar. He has obtained his PhD degree and master degree from MNIT Jaipur in structural engineering, and he has expertise in development and execution of experimental test setups for large and full-scale reinforcement, cement concrete, and steel concrete composite structures. And he is also involved as a team member in various consultancy projects of structural design, proof checking of buildings, bridges, mixed design of concrete, and testing of the reinforcement bars. And he has also completed some of the research projects, and also involved in research activity. And Dr. Pankaj, I am very thankful to you for accepting our invitation. And it's my belief that we will be having a highly storming session today on various aspects of design of the composite beams, and definitely all of us will be benefited and fortified with your expertise. So with these words, I once again welcome you all in this workshop. Thanks to you. Over to you, Arnav. Arnav?
Thank you very much, sir. Thank you very much for introducing our guest. And now, without any delay, I would like to turn the podium over to Dr. Pankaj Kumar to please begin with his session that he has so wonderfully prepared. He has shared with all of us the handouts, and I hope all of you have taken the printouts and you are ready with your pen and pencils and erasers to learn about composite beams. So, Pankaj, sir.
Yes, thank you, Department of Civil Engineering and Center of Excellence in Structural Engineering and Disaster Management, Jaypee University of Information Technology, Waknaghat. Good morning, everyone.
Good morning, Pankaj. How are you?
I'm good, sir. So today, as we know, we all are gathered here in this particular online platform, or we can say in one-day webinar on hands-on design of composite beams. First, I will take a short look of I will take a look of short introduction about composite, especially steel concrete composites, and later on we will take one example, or we will discuss one example related to steel concrete composite beams, right? So I'm sharing I'm sharing handout or presentation. Hopefully my screen is visible.
Not visible
Not
right
yet,
now.
Dr. Pankaj.
Just a sec. I think now it is visible.
Yes, yes, it is visible
Yes.
now.
Okay. Okay. Thank you. So today we will discuss about hands-on design of composite beam. First, we will take an introduction about a steel concrete composite, or we can say composite, how they interact with each other, how we can ensure the connections between steel and concrete, what are the benefits of composites, why we are using composite member instead of RCC, although RCC is also a composite, in that we are inserting reinforcement bar, or the reinforcement bar is embedded inside the concrete slab. But in case of composite, we are taking advantages of steel as well as concrete. So these are the outline of presentation. First, we will start with composite. As composite means basically when we are combining different materials or different components, or we can say different elements made up with different material, then we can call it as a composite. Next, we will discuss about composite structures. Composite structures means when we are talking about civil engineering, then most of the time we in composite we are talking about steel concrete composite. And when we are talking about steel concrete composite, it means we have two different kind of material, two different kind of component. One is steel and second one is concrete. So the connection between steel and concrete is one of the important parameter to ensure the integrity between steel and concrete. Therefore, next we will discuss connection between steel and concrete, and after that we will discuss characterization of connection, because whenever we are ensuring connection between steel and concrete to make them composite, usually there are different kind of connectors available in market, and we can also develop different kind of connector, but how we can take the best advantages of each part, as well as the perfect, or we can say complete capacity utilization of connections also, and based on our requirement. Like sometimes if we are looking into the performance, sometimes we are looking into the strength, sometimes we are looking into the both of the aspect, both of them. In that case, which kind of connections are most suitable, because different kind of connectors at the interface level of steel and concrete have different kind of properties, and at the end we will discuss one design example. So this is the common, usually whenever we are looking into the composites in steel concrete composites in civil engineering aspect, firstly they are invented to accommodate large span, because whenever we are looking into the largest spans, whenever we are looking into the largest spans, there, if we go with RCC, in that case there is lots of challenges, like the geometrical requirement and all there, and because of that there is, and the size is, and economy is also a concern. Therefore, at uh, at location where usually tension occur, at that places we are inserting steel component or steel elements, and at locations where compression occurs, on that location particularly we are inserting concrete. So this is the one of the typical example of steel concrete composite bridge, in which the particular beam section is made up with steel section, and the deck slab section is made up with RCC, and it is resting on RCC piers. So this is the in the previous picture, uh, if you are looking into the picture, there is connection is not visible at the interface level of steel and concrete. So if we are looking into the classical form of connections, usually at initial development stage, likewise 70 years back in 1950 or early 60s, they started to make connectors, or we can say connection between steel and concrete at the start of composite steel concrete composite. They make it with reinforcement bars, but after that they found some challenges in it. Likewise, there is resistance issue are also there. There is some uplift pressure also they are getting, because there is no resistance section. Therefore, they introduce headed kind of connector to ensure the connect integrity between steel and concrete. Therefore, in this particular picture, one steel beam is available, and at the top flange of steel I section, the mechanical shear connector, specially headed stud are connected in two rows. These particular two rows are in line. We can connect them in staggered patterns also. So this is also one of the one example of the steel concrete composite bridge. If you are looking into this particular, it is likewise it is in construction stage. Therefore, between two piers there is some probe construction is also the probes are also, vertical probes are also inserted, that is known as vertical shoring, because usually we are putting vertical shoring because to avoid excessive deformations or excessive deflections in steel beams, because as we know, initially when we are pouring concrete or we are placing concrete over steel beam, the concrete before getting its strength, it is acting as a dead load over steel beam. Therefore, steel goes under deformation in initial stage also. So after certain time period, once the concrete is hardened, after that concrete is also take some concrete is also contribute in strength, but at initial stage there is no strength available. Therefore, the steel sections goes under deformation. To avoid that, to avoid the deformation in steel at initial stage, usually we are using propped construction. And if we are not using these vertical shoring, in that case we can say it is a unpropped construction kind of construction. And sometimes we are using cambering also, but usually for when moment occur at the connection, in that case cambering is not possible, and usually it affects the aesthetic view also, and it is difficult to provide a camber in such large sections. Therefore, usually we are going for propped kind of constructions. This is also one of the typical example of, as we know, we can use steel, concrete, composite in different component likewise, or we can construct different kind of structures. The previous some examples are related to steel, concrete, composite bridges, but nowadays because of space availability and all, the people are using steel, concrete, composite as a and construction element in residential buildings also, commercial spaces also, and sometimes if we are looking into the warehouses also, in warehouses also, this is one of the typical example of steel, concrete, composite beam floor system. In this particular case, usually they are using passive reinforcement. If you are looking into this closely, if you are looking closely into this picture, there is one profile sheet is provided over the steel beams, and as we know, there is also some space constant and height constant. Because of there, we have lots of flexibility in steel, concrete, composite construction. Likewise, if you are looking into the pictures in secondary beams, if you are looking into the secondary beams, there are holes are provided in web sections so that you can ensure all the electricals, wire conduit and all, and you can utilize the space properly. Therefore, next is when we are looking into the steel, concrete, composite, then we have three different kind of, especially we have two different components. One is steel and second one is concrete. If we are looking into these two component, we have different element in these component. If we are looking into the steel, we have, especially if I'm talking about I sections, in I sections we have flange, we have web section. Especially if I'm looking into the concrete, we have reinforcement, we have plain concrete also. So first we will discuss properties and some of the advantages, disadvantages and behavior of steel, and after that we will go for composite. So if I'm looking in this in composite construction, usually we are using steel and we are using different kind of sections. Some of the common sections are like I sections. Sometimes we are using channel sections. Sometimes we are using angle section based on our requirement and sectional property requirement, or we can say based on moment rotation requirement, or we can say ductility requirement. So if I'm looking into the advantages of steel, as we know, steel has a good reliability, it has industrial behavior, it requires lesser construction time. Because of that, we are getting greater erection speed. As we know, steel has higher strength in compression as well as in tension. The strength in compression as well as tension in almost similar, therefore, and it is, if we are looking into the strength wise, it is lightweight in nature. Likewise, if you are if as a civil engineer, if I'm comparing steel and concrete, so from same cross sectional area we are getting more strength, therefore we can say we are getting lighter structure. And we can say that usually we are getting steel section from workshops, therefore we can say there must be a uniformity in section, there must be durability, and there because of that we are getting great better performance in case of steel. And if we are looking into the stress strain behavior of steel, as we know, if we are looking comparing steel with concrete, in one key, if in concrete, usually we are considering elastic limit up to 40 to 50% of ultimate, but in steel, we can say up to 70 to 80%, approximately up to the 80% of ultimate is your elastic range. Therefore, we can say steel have better elasticity, and of course, ductility is again an important parameter because of ductility, it is the steel is very good in uh, seismic performance, especially it shows warning before failure, and as we know, it is we can add we can add some sections based on our requirement. If we are increasing size of section, that is also very easy in steel as compared to concrete, because whenever we are going for retrofitting or strength enhancement for concrete, in that case we required a connection between old and new concrete. If we are adding some different material, in that case also we require some connection, but simply by weld we can ensure a well riveted and bolted kind of connection, we can enhance the structural strength also, and it is also reusable, and mostly we are using steel for long span construction. Similarly, steel also have some disadvantages like high maintenance cost. It is more susceptible to corrosion, less fire resistance. It shows sometimes it shows local as well as local buckling also. It requires high initial cost, and sometimes people are avoiding it in residential building just because of aesthetics. Therefore, these steel concrete composite kind of structures are more often in commercial as well as highway projects, and as we know, it requires skilled labor for connections as well as for maintenance also. Similarly, concrete, when we are looking into the reinforced concrete, usually we are it is a cast in situ concrete, and we, as we know, there is some advantages of concrete also available, like we we can mold it in any shape and size just because of its semi liquid kind of natures. And if we are looking into the, especially into the advantages and disadvantages, the availability of materials, we can get it from locally, similar to steel as compared to steel sections. Steel section we have to order it, and we will get from some industries only, but we can generate or produce concrete locally also, and it can be molded in any shape, as I told you. And skill labor are also not required. Similarly, if you are looking into the steel connections and all, they require skilled labor. And again, as compared to steel, reinforced concrete or concrete has better fire resistance. And again, if we are looking into the some aggressive environmental condition, as compared to steel, concrete provides us better durability, and also it acts as a thermal insulator also, and it requires less maintenance and less maintenance. Similarly, if we are looking into the disadvantages, there is no tensile strength. The concrete is very good in compression, as we know, but it shows very less strength in tension. Therefore, these are the some disadvantages of concrete. And if we are looking into the behavior as compared
Dr.
to
Pankaj,
yes.
sorry, uh, somebody else started presenting their screen. I just request everybody to keep their presentation mode off. Thank you. Please do not share your screens. Sorry, Dr. Pankaj, for interrupting. Please continue.
So similarly, if we are looking into the behavior, as we know, as compared to steel, the strain is also very less in concrete, as well as if we are looking into the compressive strength also. Usually, as I told you, in case of steel, the elastic behavior is very high stress range as compared to when we are comparing it with concrete. Similarly, when we are looking into the elastic behavior of concrete, we have very less stress range, like 40 to 50% of ultimate. That is again a challenging part. And next is steel concrete composite. Now we know that all the advantages, disadvantages, and behavior of steel, as well as advantages, disadvantages, and behavior of concrete. Now we can utilize steel and concrete based on their. So here I can say, if I'm looking into the definition of composite, I can say combination of two and more materials that have quite different properties, and these different materials work together to give the unique properties to composite materials, and they can easily be differentiated from each other. So if I'm looking into the definition of composite, we can say it is a combination of two and more materials. So here, now we know we have two different material. One is steel and second one is concrete. So we can take the best advantages of steel. As we know, steel is good in tension as well as in compression, but concrete is good in compression but weak in tension. So in compression zone, we can provide concrete because of economy, and in tension zone, we can provide steel because of high strength, high tensile strength. So there is a typical picture of steel concrete composite beam. So when they are connected, we have different method of connections. Likewise, how we can ensure the connection between steel and concrete. For that, we have either we can connect it by mechanical connector. In mechanical connectors also, we have different kind of connector. Similarly, we have some kind of adhesive connections between steel and concrete, and based on requirement also we can decide. So as we know, in most of the cases, if we are looking into the steel concrete composite, always connection are used at the interface level just to transfer the forces from one phase to another phase. So therefore, most of the time, if there is axial kind of forces, in that case, they are always subjected under shear only, because as we know, out of plane compression and tension is shear. Therefore, most of the time they are subjected under shear only. So therefore, whenever we are talking about connectors, we are talking about shear connectors only. At some cases, if the deflection is very high, in that case they are subjected under bendings also, but more or less they are subjected under shear only. And based on interaction, we can decide how much amount of slip we are allowing at the level of interface. So here we will talk about some advantages of composite over conventional reinforced concrete. So first is high strength to unit weight ratio. If we will construct a RCC beam with same moment of inertia, we required very high amount of concrete, and if we are go for steel, we require lots of money. Therefore, in most of the, to take the best advantages, we are using composite, and because of composite, we are getting high strength to unit weight ratio. And next is flexibility in construction is also available in case of composites, and ease in constructions, is to repair also, and is to retrofit also, and partially reusable also. As we know, if there is a dismantling going on any kind of steel concrete composite member, right, we can use steel. Steel is also reusable material. Similarly, right now, because of the advancement in concrete, and the concrete is also reusable right now because they are using recycled aggregate and all. And next is high ultimate strength, and one more thing is high durability, and we are getting better ductility as compared to concrete. That is again one of the advantage of composite over conventional reinforced concrete. So this is also one of the advantages of concrete, because of these openings available in steel beam web, we can insert all the utility pipes, all the arrangements within beam portion only. This is not possible with conventional reinforced concrete systems. So this is the typical definition of composite when we are combining two or more than two different materials to take the best advantages of its positive attributes. They're known as composite. And this is the comparison between composite as well as non-composite sections. If you are if you are looking into the pictures, left side is non-composite section and right side is composite section. In non-composite section, concrete slab is just placed over steel beam, and in second right side part, the concrete slab is connected with steel beam with the help of headed shear connector. So if you are looking into the deflected profile also, we are getting more deflection in case of non-composite section as compared to composite sections. If you are looking into the composite section, that is usually defined by relative slip at the level of interface when we are applying loading over it. If you are looking at the end or at the end of, or we can say above the support, if you are looking above the support, there is a slip between steel and concrete. If concrete deflect more, if the curvature is more in case of concrete, in that case it will go out. And if you are looking into the steel, if you are getting less curvature, in that case the movement between there is a curvature difference between steel and concrete, therefore we are getting relative slip at the level of interface. It is, and similarly if you are looking into the composite side, that is on right side, at the end, at the level of interface, there is no slip, or we can say relatively a little amount of slip, or very less amount of slip. That is the basic difference between composite as well as non-composite. So why here if we are looking into this picture, here I am showing more deflection in non-composite beam as compared to less deflection in composite beam. Let me show you how. If you are looking over here, if I am taking a section with depth d, as we know the moment of inertia is
हेलो
direct.
सर
Yes,
सर इसके आगे वाला फिर से समझाओ ना, ये समझ में नहीं आएगा इसके ये स्लाइड समझाओ ना फिर से.
this one.
यस सर.
In this particular picture we have a simply supported steel concrete composite beam. In left side part I have non-composite action, and right side I have composite action. The why in left side is non-composite, because if you are looking into this particular section, at the top it is a concrete slab and at bottom it is a steel slab, typical I section, right? And on right side also it is same, but at the level of interface on the at top flange, headed stud are connected to steel section and embedded in concrete, right? If I'm applying any amount of loading over it, in that case I will get some deflection. As we know, if we are applying any loading over any structural member or any flexural member, we will get some deflection. But in case of non-composite, we are getting more deflection as compared to composite section. It's shown in
Yes,
figure also. And similarly, if there is no interfacial connection at the level of concrete and steel, in that case we are getting some amount of slip at the interface level, because there is difference in curvature, right?
Yes, sir.
Still different independently and concrete deflect independently. Similarly, if I'm looking into the composite, both deflect in same manner. Therefore, we are not getting any amount of relative slip at the level of interface, right? So that is basically difference between composite and non-composite sections. So next, here here is a point like I'm showing more deflection in non-composite beam as well as less deflection in composite beam. Why it is? So if you are looking into these two sections, as we know, whenever we are looking into the deformation, we are talking about moment of inertia, right? It is inversely proportional to moment of inertia, right? Deflection is inversely proportional to moment of inertia. So if I'm taking any kind of section, either it is a rectangular section, or I can say prismatic section, or a I section, at every time we know there is some coefficient, but moment of inertia is directly proportional to d power 3, right? So similarly, if you are looking here, if I am putting directly concrete slab over a steel beam, or if I am putting two different component one over each other without any interaction, in that case, I will get the depth is equals to 2d. But the moment of inertia is d cube plus d cube, right? So therefore, moment of inertia is directly proportional to 2d cube, because there is no interaction between steel and concrete. So if I'm taking same section with connection, it means they are acting as single unit. So in that case, the total depth is now 2d. It is 2d. So therefore, the moment of inertia is 4 times of previous one, right? It is now 8d cube. So therefore, you are getting considerably lesser deflection as compared to non-composite section, right? Because as we know, deflection is inversely proportional to moment of inertia. So if there is a composite action between steel and concrete, in that case, the D is here not, it is independently D for concrete and D for steel. It is combined. So it is 2D. Therefore, I is 8D cube, directly proportional to 8D cube. It means, and previously it was for same section, if there is no connection between them, in that case it was D cube plus D cube. Therefore, it is 2D cube. So that is why composite are more economical. So next is connection. So we can classify connection between steel and concrete based on 4 different criteria: based on member function, based on degree of connection, based on degree of interaction, and material based. So based on member function, likewise, if we are looking into any structure, we have different member, and function of different member are different. So we can construct any section with the help of composite, but we can classify connection based on member function. Likewise, first one is a column in which concrete is encased with steel hollow core steel circular section, right? Second one is also a column section in which concrete is partially confined with steel I section. Third one is typical example of steel concrete composite flexural member or beam section, in which concrete is placed over steel I section and connected with added stud shear connector. And next one is also one of the typical example of steel concrete composite floor system. As I told, as I saw in previous slides, at a third, fourth slide, it was available. Like if we can provide some passive reinforcement, we are providing some passive reinforcement below the concrete slab, or we can say floor system. So this profile sheet is your passive reinforcement, and the arrangement looks like this. So we can arrange it at different angle also. Based on that, we can calculate effective section of composite member also. In case of profiles of it, we can arrange it at in longitudinal reefs placement also. We can arrange it in transverse reefs placement also. We can it placed in oblique reefs placement also. Likewise, this is in this particular case, if I'm looking into the cross section, it is longitudinal placement. I can play, if I'm rotating it at 90 degree, I will get different soffit height, and if I will place it at an inclined angle, I will get different soffit height. That is known as your haunch height. This is also one of the typical example of composite beam column connection. So next is, this is based on member function. Next one is degree of connection. So degree of connection means, based on degree of connection, we can categorize connection onto different categories. One is partial shear connection, second one is full shear connection, and so if, and third one is no shear connection between them. So if you are looking into it, the degree of connection totally a strength based criteria in which we are ensuring connection between steel and concrete, whether there is a connection available, there is no connection available, and if the connection is available, then the strength of connection is higher than concrete or higher than steel or higher than both of them. If the strength of connector is higher than concrete or steel, in that case we can say the connection is full shear connection. And if the connection strength is lesser than minimum of concrete or steel, in that case we can say it is partial shear connection. You got it? So as we know, degree of connection is a strength based criteria. It means we are calculating strength of three different members. One is strength of RCC or strength of concrete slab, second one is strength of connector, and third one is strength of I section. So if the strength of connector is higher than either concrete or steel or both of them, in that case we can say the connection is full shear connection, because before connectors fail, either your concrete will fail or your steel will fail or both of them will fail. That is known as full shear connection. So similarly, if the strength of connector is lesser than minimum of either steel or concrete, if it is lesser than minimum of steel, suppose the strength of steel is maximum, strength of concrete is lesser than steel. So therefore, if the connector strength is lesser than concrete, in that case we can say the connection is partial shear connection. And as I told you, we are defining it based on strength. Therefore, degree of connection is a strength based criteria. Hopefully you got it. Yes. So here it is visible. So here, if you are looking into the first figure, it is P concrete is higher than P steel. It means the stresses in steel are fully developed, but now right in first figure, right now we are utilizing only some amount of strength of concrete. So in that case, if the strength of shear connector is more than or equals to the strength of steel, in that case we can say it is a full shear connection. Similarly, if you are looking into the second case, in second case the strength of steel is more than strength of concrete. So therefore, here it is visible, and the strength of shear connector is more than concrete. So before failure of an, so first the concrete will first fail. So therefore, strength of shear connector is higher than concrete. Therefore, we can say it is also a example of full shear connection. Similarly, if you are looking into the third, so in that case, P concrete is, strength of concrete is also higher than strength of shear connector, and strength of steel is also higher than strength of shear connector. Therefore, the shear connector will fail first. So this is known as partial shear connection. So therefore, whenever we are applying degree of connection can go beyond 1 also. Similarly, if we are looking into the degree of interaction, maximum value of degree of interaction is 1 and minimum value is 0. That is, so in degree of interaction is a stiffness based criteria. Therefore, we are defining it by slip at the level of interface. If I'm talking about slip, as we know, the change in slip is the difference of strain in steel and strain in concrete. If I'm considering in x direction, therefore if I'm denoting slip by s, then the ds by dx, which is change in slip, which is equals to strain in steel, difference of strain in steel and strain in concrete, es minus ec or ec minus es, anyway. So that is your strain. So based on slip or change in slip. So based on that, we can define three different kind of degree of interaction. One is full interaction, second one is partial interaction, and third one is no interaction. In full interaction, what happened? The relative slip at the level of interface. Although we are applying some connector at the level of interface, but if we are saying that there is full interaction, it means the stiffness of connection is infinite. As I told you, degree of interaction is a stiffness based property. Therefore, the stiffness of at the level of interface is infinite. So there is no change in slip at the level of interface. If you are looking into the full interaction strain diagram for full interaction, there is no change or there is no change in gradient of strain line, right? So next is partial interaction. In partial interaction means we have some kind of connector at the level of interface, but the stiffness is, we can define the stiffness of interface with the help by some amount. Therefore, there must be some change in slip. And in most of the practical condition, we have partial interaction between steel and concrete. It means we are getting some amount of slip. They are not behaving independently, but there must be some amount of slip. We cannot ensure full interaction. And third case is about no interaction. If both of them are not connected, there is no connection between steel and concrete, that in that case, steel will behave independently. That's it is shown in last figure, and concrete will also behave independently. So this is about degree of interaction. Next is based on connection material. As I told you, we have usually in practice right now in practical purpose, we have two different kind of material to ensure the connection between steel and concrete. One is threaded connector, mechanical shear connector based, and in mechanical shear connector we have different kind of connectors, like channel shear connector, angle shear connector, T, perfo bond, Y kind. But one of the common example is threaded shear connector, which is shown in left side figure, and second and right side figure shows the connection between steel and concrete with the help of structural adhesive. So because there are some advantages of mechanical shear connector and there are some advantages of adhesive connection also. As I told you, whenever we are applying mechanical shear connector, when we are applying mechanical shear connector, we are getting semi-rigid kind of connection or flexible kind of connection. But when we are applying structural adhesive at the level of interface, it means we are our stiffness goes up to near about infinite. So in that case, we can say there is no interfacial slip visible at the level of interface. So as I told you, when I'm discussing connecting material, as I told you, one is mechanical kind of connector. They fall either under semi-rigid kind of connector or flexible kind of connector based on degree of interaction, and one is rigid kind of connection, that is usually we can ensure by adhesive bonding. For that we can use any kind of epoxy bond, and this is also explained by load relative slip curve. And if you are looking into the stiffness for flexible connection with brittleness, it is like The stiffness of load deformation, load slip curve is very less as compared to semi-rigid and rigid connector. Similarly, if we are moving upward side, we will get semi-rigid kind of connector, and at the end we will get rigid kind of connector. Of course, rigid kind of connector are very brittle in nature because they are not allowing any kind of relative slip at the level of interface. It means the nature of connector is brittle. If the nature of connector is not brittle, it means they will allow some amount of stiffness at the level of connectors. And next is structural demand. For a structural member or structure, requisite stiffness and adequate strength and sufficient ductility. These are the three demand of any structural member. So if you are looking over here, so we can ensure the requisite stiffness based on material, and that is based on elastic modulus, because as we know the slope of stress strain curve is elastic modulus, and that represent your elastic modulus, and shape of structure element also. Similarly, if I'm looking into the adequate strength, that is based on member function, which is truss. Some of the typical example are truss, beam, column, slab, beam, column connections and all. And if different kind of loading also affect the strength of member also, likewise, either whether it is a force kind of loading or displacement kind of loading. Some of the typical example of different kind of loading are static, cyclic, reverse cyclic, dynamic kind of loading, impact loading, wind loading, and earthquake loading. And next one is the demand is sufficient ductility. So whenever we are looking into a composite material, we are looking for three different things. One is required stiffness, requisite stiffness, adequate strength, and sufficient ductility. These are the three key parameters to design a structural member at any level. The ductility, if you are looking into the ductility also we can ensure on the level of material, and on the level of cross sections also, on the level of member also, and at the end, if we can ensure the ductility on these three, we can get the ductility at the level of structure also. We can ensure the material ductility by stress strain curve. We can ensure the cross sectional ductility by moment curvature curve based on value of curvature, and we can ensure the member ductility based on moment rotation curve, and we can ensure the structural ductility based on, at the end, if we are applying any kind of force over structure, we are getting some deformation, therefore we can ensure material ductility with the help of force deformation curve. So and this is about structural demand, stiffness and strength influence. If you are increasing the strength of connection, you are getting more strength, but you are getting lesser ductility. So based on that, three different kind of structures are defined on force deformation curve. As I told you, at the end, we will ensure the ductility in structural member. So design criteria for ductility: one is analysis requirement, and second one is detailing requirement. Ductility, as we know, ductility is the ratio of total deformation to yield deformation. This is the point from where initial yield start to ultimate point. This is the ratio of deformation between these 2 points. So therefore we are calling steel as more ductile as compared to concrete, because we are getting all very good ductility in case of steel. And ductility of structure depend upon, as I told you, it is depend upon material, cross section also, member also, and at the end we can ensure it in structural member also. And next is different kind of shear connection. As I told you, we can ensure the composite action between steel and concrete with the help of connection. If I'm looking into the connection, we have different kind of connections. Based on material, we can classify on two different category. One is mechanical and second one is adhesive bonded. In mechanical, we have different kind of connector, like as I told you, channels connector, L-shaped connector, T-shaped connector, headed, demountable kind of connector. It is a new concept. It emerged in last 10 to 15 years. Demountable kind of connector, perfobond kind of, T-perfobond, Christobond, Y-shape, J-shape, and usually based on the requirement, the researchers are developing different kind of connectors. And last one is adhesive bonded, because whenever you are inserting any kind of mechanical shear connector at the level of interface, you are getting some amount of stress concentration at that level. To eliminate the stress concentration issue, you can use the adhesive bonded, but adhesive bonded connections also have some limitations. Likewise, likewise, we can ensure the connection only between the interface. In mechanical shear connection, the connectors is always embedded inside the concrete. Therefore, we can rely on the superficial property of concrete as well as steel. That is an issue with adhesive bonded kind of connection. And if you are looking into this is the typical load slip behavior of composite connections. And these are the typical pictures of different kind of mechanical connectors. This is the first picture is angle shear connector. If you are looking over here, the placement of angle we can made with by two different type. One we can put parallel at top, and one we can put parallel at bottom. So if you are putting in this particular in first position, or I can say in figure A position, in that case you will get better resistance. And if you are putting on second, in that case you will get lesser resistance, or you can say you will get more uplift pressure. And next one is channel shear connector. As we know, that whenever the embedded part is more in concrete, in that case we will get more strength of connection. That is, so we can say height of web is also one of the influencing factor in channel connector. Width of web is also thickness of weld, otherwise they will fail in buckling. Concrete compressive strength is also, and deck geometry also. So this is the typical kind of channel shear connector. And the orientation of channel shear connector is also one of the important parameter. From if you are applying loading from one direction, then you must ensure that orientation of channel shear connector also, in which direction it is more suitable. If the open flange are towards loading side or opposite to the loading side. So this one is the headed shear connector. Why most in common practice people are using, or in practical practices the engineers are using headed shear connector, because it has uniform resistance. The shape of headed shear connector is circular, therefore it has uniform resistance in all direction. And therefore there is, if you are looking into the any kind of shear connector like channel shear connector and angle shear connector, there must at the corners we will get stress concentration. As we know, the this is total design load. And imposed load, if I'm looking into the imposed load, it is 3 multiplied by 3 meter, because the spacing between two beams is 3 meter. It is 9 kilonewton per meter. Again, partition wall, it is 1.5 into 3, which is 4.5 kilonewton per meter. And the total design live load is 1.5.
Excuse me, sir.
Yes.
Can you explain the load from partition wall? Why are we considering that? Assuming
It is given in question. There is, so usually we are considering load which are given in question only.
so why do we consider partition wall in case
if there is if there is any given in question, if it is not given, then we can directly eliminate it also. There is no issue. it is about load consideration and possible combinations of load only, not more than that. It is 20.25, hopefully. So therefore total load is, it is 37.086 kilonewton per meter, right? 20.25 plus 16.836, right? 6538, right? So from, if we know the load, we can calculate the moment also. So if I'm looking into the moment at construction stage, as we know, the loading is load is UDL kind of, because all of the load are uniformly distributed. Therefore, we can say bending moment is usually WL square divided by 8. Therefore, for construction stage, the load is, it is 17.961. 17.961 multiplied by length. Length is also given. So I think question it is written like 7.5 meter, right? But here, to make it simple, I am considering 10 meter only. So we can say it is, we will get a value of around 224.51, right? Kilonewton into meter, right? Similarly, for composite stage, we can say it is 37.086 into 10,000 square divided by 8, same WL square by 8. So here we can say it is, so here we can write, because we are putting it in kilonewton per meter, na? Therefore we can, so it is 463.575 kilonewton into meter. So next one is about classification of composite section. So here we can classify our section, whether it is plastic section, compact section, semi-compact section, or cylinder section. As we know, IS 800 specify based on B by TF ratio, whether the section is plastic, compact, semi-compact, and cylinder section. The values are given here. IS 800, you can check it from IS 800 2007 part 2 also. So as we know, plastic section, those can develop plastic hinges and have rotation capacity required to failure by formation of plastic mechanism. This section fall under plastic category. Similarly, if I'm looking into the compact section, can develop plastic moment of resistance but have inadequate plastic hinge rotation capacity. This section fall under compact. If extreme fiber in compression can reach up to the yield point but cannot develop plastic moment of resistance, such kind of section fall under semi-compact section. And one more is here, that is cylinder kind of section. They are buckle locally even before reaching yield stage. So these are the B by T ratio. Here, if you are looking over here, B is half of flange width only. It is not complete flange width. Therefore, if I'm looking over here, as we know, in this particular problem, it is given that ISMB 450. So thickness, area of cross section, weight, moment of inertia about major axis and minor axis, section modulus, and radius of gyration are given. So here it is, and here if I'm looking into the B by TF ratio for particular section, here value for B is the total flange width is for ISMB 400, it is 150, so we can say it is B is 150 divided by 2, and value of TF is thickness of flange, which is 17.4. It is given in question, so therefore we can say these are the properties of ISMB 450. So it is 4.31. And if I'm looking over here on classification of section, it is, so 4.31 is less than 7.9 epsilon, where epsilon is ratio of square root of, epsilon is a constant which is the square root of 250 divided by yield stress of structural steel, which is also specified in question, and it is 250. Therefore we can say it is lesser than 9.4 into epsilon, and value of epsilon is again 1. Therefore we can say it is 9.4, and it is true. Therefore we can say the section is, and for plastic, but before ensuring plastic we have to check it for web with neutral axis at mid depth also. Here d by t is less than equals to 83 epsilon. So if I'm looking into the d by t, so here d is 450, and especially here it is defined that d is the center to center distance between flanges. So it is 450 divided by thickness of web. Here it is web, because right now we are talking about web. It is 9.4, so we can say it is approximately 47.87, and which is less than 84 epsilon. Value of epsilon is 1, therefore so we can say the section is plastic section, right? So next step is check for the adequacy of the section at construction stage. So design moment in construction stage we have already calculated, it is 224.51 kilonewton into meter. So moment of resistance of section is, it is stress multiplied by design stress multiplied by, if I'm talking about multiplied by section modulus, which is Zp, plastic section modulus. So here it is Fy is design is, if the yield strength is 250 for steel, in that case if I'm applying partial safety factor, as we know as per IS 800, the partial safety factor for steel it is 1.15, and if I'm looking into the Zp, so the section modulus is given in metal section properties of ISMB 450, so it is 1350, 0.70 into 10 power 3, and if I'm multiplying it by shape factor, I will get plastic section modulus. So for, as we know, for I section it is 1.14. So I can say it is 334.74 into 10 power 6 Newton into mm, or 334.74 kilonewton into meter. So this is the moment of resistance of steel section. As we know, during construction stage, all the load must be beared by steel section only, and it is more than 224.51. So in that case, we can say it is safe, right? So next is check for lateral buckling of the top flange during construction stage. Right now we are talking about only construction stage. So as per IS 800, if you are looking into the IS 800, so first we will calculate extreme fiber bending compressive stress corresponding to elastic lateral buckling moment. So that is defined by, first we are calculating, to calculate the moment, first we are calculating extreme fiber bending compressive stress corresponding to elastic. Is it visible?
Yes, sir.
Lateral buckling. So which is given by a formula which is suggested in IS 800. On, if you are specifically, if you are looking into the clause, it is 8.2.2.1. It is FCRB, which is equals to 1.1 pi square E divided by LLT divided by RY square bracket start 1 plus 1 by 20 bracket start LLT divided by RY divided by HF upon TF square and power 0.5. This is the formula. So if I'm putting all the values, just a second. If I'm putting all the values in formula, then FCRB is equals to 1.1 multiplied by pi square, which is 3.14 multiplied by 3.14 multiplied by E, which is, as we know, for steel, it is 2 into 10 power 5 divided by LLT. It is the distance between point of contraflexure, and as we know that the case is simply supported. In that case, we are considering it as 1, and the value are also given in clause number 8.2.2.1 for different kind of conditions also. It may vary from 0.7 to 1. So it is, as we know, the length is 10,000 mm, and the RY value of RY is also specified for properties of ISMB 450, which is 30.1 square, and it is 1.1 by 20, and here we have same 10,000 divided by 30.1 divided by HF, which is 450 divided by TF, which is 17.4 square and power 0.5. So from here, if you will calculate, you will get a value around 64.26 Newton per mm square. Right? So next we will calculate from FCRB, we will calculate design, bending, compressive stress, FBD, that is FBD. And for FBD there is a lengthy formula, but there is two table available for if the section is fabricated and if the section is hot rolled. These are available in IS 800 on table number 13A and B. Based on alpha LT. Alpha LT is coefficient for rolled steel section, it is 0.21. And if you're specifically, if you're looking into the formulas, I can write it for you. It is gamma LT Fy divided by gamma M0, that is partial safety factor for material, and here gamma LT is equals to 1 upon phi LT plus phi LT square minus lambda LT square power 0.5, and it must be lesser than and equals to 1.0, and here phi LT is equals to 0.5 1 plus alpha LT bracket close bracket start lambda LT minus 0.2 plus lambda LT square. Or we can directly if you want to calculate, you can calculate from here, and if you want to write the value for bending, design bending compressive stress directly, you can take it from IS 800 table 13A and B. 13A and B. 13A is for rolled steel section and 13B for welded steel section, right? And for those alpha LT is different. Alpha LT is 0.21, and here for alpha LT is equals to 0.49. So if you are looking into the table 13A, because usually we are considering ISMB 450, we are directly purchasing it from fabricator, and that is rolled steel section. So we can consider alpha LT is equals to 0.21, and for that table 13A, we can check the value. And if I'm looking into the values at level of 70, it is 56.8, and at level 60 it is 50. It is given in table 13A, you can check it. Because of the time availability and time doesn't permit, otherwise I can show you, because we have last 30 minutes only. That is why I'm going a bit fast. So here I can say FBD is equals to, we can calculate the value at the level of 64.26 with the help of interpolation, and which is 50 plus 56.8 minus 50 divided by 70 minus 60 and multiplied by 64.26 minus 60. So from here we will get a value around 52.90 Newton per mm square. So this one is design bending compressive stress, right? So this is design bending compressive stress. So here we can calculate maximum stress at top flange also. So because as we know, the bottom flange is restrained on some support, but top flange is not restrained. Therefore, we are calculating maximum stress at top flange, which is FCB, which is equals to, here it is, as we know, the moment is equals to 224.51, and if we are looking into the section modulus, which is 3, moment of inertia, which is given in question, which is 10 power 6, and if I am looking into the total depth of section, which is 450, so I can say value I upon y. So m upon I, it is directly m upon I into y. It is, as we know, the stress is m upon I into y. So therefore it is 225. So it is 225, and I can say it is in kilonewton into meter. So therefore I'm multiplying it by 10 power 6. So I will get a value around 166.22 MPa. So as we know here, the design bending stress is 52.90, and the maximum stress at top flange is 166. So therefore we have to revise the section. So now, or we can provide some support, lateral support, at the time of construction, so that the beam will not buckle during construction stage, right? Because after some time, if the concrete is taking some strength, in that case there must be some change in stiffness also. Initially the steel section stiffness is also very low, therefore, and there is local buckling also. So to prevent the buckling, usually we are providing some lateral support at some distance to ensure that to prevent the section from buckling, right? So we have to calculate the resistance again. We can apply the same formula. And now what we are doing in FCR, right now, suppose this is the beam and the span length is 10 meter. So as we know, if the length is unsupported, as I told you, usually we are providing some probe. I have shown some example related to vertical soaring to you at some places. In my third or fourth slide, there is some vertical, some probe are provided at intermediate span. These probes are provided just to avoid the buckling. So if the span length is 10 meter, and as we know the design strength is around 52.990, and FCB is 166.26, right? 166.26 to 2 MPa, and the design strength was 52.90 MPa. Therefore, we can provide some props. So we can select it accordingly. Suppose if I'm considering 3 probe, in that case, my length available is 2 meter only. 2.5 meter only. So therefore, now I have to calculate FCRB by 2 meter only. So as we know, in FCRB, we are using, just a second, in FCRB here, instead of 10,000, we can now put 2,500 over here. Rest all are the same, therefore we will get a different value. So from here, if you are putting, instead of 10,000, if you will put 2,500, you can take 2 probes also. So based on that, you will get 3333 also. Over here you can put 5 also. Based on that, you will get 2,000 also. It is up to you how much you want to provide to avoid the local buckling. At the end, you have to satisfy stress criteria, which is the maximum bending stress must be more than stress in top fiber. It is the condition. So if we are instead of 1000 if you're putting 2500, you are getting a value around 166.22 m. Sorry, you are getting a value. Sorry, you will get a value around 398. 398.39 MPa. So from here we can again calculate FBD, and which is again given in table. So from table, if we are looking into it, looking into the FCRB value equals to 319.39, it is equals to 400. So here for 400 we will get a value around 184.1 MPa. Okay, and as we know, 184.1 MPa is more than 166.22 MPa. Therefore, we can say now the section is so safe, or these resistance are to be kept till concrete hardened. So we will provide these probes up for a time interval up to which concrete is hardened, right? So next is about effective width. It is, I think, written somewhere. Yes, it is. So it is about effective width. So for if bending moment as composite stays, it, as we know, bending moment at composite stage we have already calculated. It was 463.575 kilonewton into meter. And for effective width, we have two different approaches. One we can calculate by Euro code 4, and there is one more similar approach which is known as Ansurian approach. So we can calculate from both of them, or Ansurian's approach. So we can calculate, as Eurocode suggests that the effective width is 1/4 of span divided by 4, and here span is maximum distance between point of contraflexure. So we can say it is effective span divided by 4, right? And we have one more constant in effective width, which is center to center distance between beam. So it means it is be effect, either it is span by 4, as we know in our case it is simply supported, so it is 10,000 divided by 4, so we can say 2,500 mm. And here also, if we are looking here, so center to center distance between beam, which is, as we know, it is 3 meters, so it is 300 mm. If there is, we have some continuous support kind of thing, in that case we can calculate it by, if we are writing B effective is equal less than and equals to T adjacent on left side plus T adjacent on right side divided by 2, or less than and equals to 2T edge if it is available at edge. So here we can say from minimum from these two, we can say it is 2,500 mm. So there is one more approach which is Ansurian approach, and it is based on T adjacent divided by LC ratio. If it is less than 1, there is a different formula, and if it is more than 1, there is a different formula, and it shows little bit conservative results as compared to Euro code 4. So it is B effective by T adjacent divided by 2 equals to 1 minus 0.6 T adjacent divided by LC. If T adjacent by LC is less than equals to 1.0, and if it is more than 1, in that case it is 0.2 LC. So it is little bit conservative because earlier we are taking 0.25. So next is location of neutral axis. So as we know, we have to calculate to calculate the location of neutral axis, we have to calculate the ratio of stresses, which is, as we know, steel. In steel, we are considering 0.87 Fy, and in concrete, we are considering usually, if we are looking into the equivalent area of stress, we can say it is 0.36 FCK, right? So it is 0.87 into Fy is 250 divided by 0.36 multiplied by FCK is 30, so we can say it is 20.1. And the cross section area for steel, it is given, it is 9227 mm square. And if I'm converting it to equivalent to determine the position of neutral axis, if I will convert it into equivalent concrete, in that case it is 20.1 multiplied by 9227. It is modular ratio kind of. So it is 1.85 into 10 power 5 mm square. So, and B effective into ds, which is, as we know, that earlier we know that this distance available between center to center distance available between these two supports is 3 meter here, 3 meter here also, 3 meter here also. But as we know, the effective width is only 200 and 2500 mm. Therefore, B effect here we are considering 2500 multiplied by ds, which is the depth of slab, and we assumed it as 125. Therefore, it is 2500 multiplied by 125, which is 3.13 into 10 power 5 mm square. So as we know, this one is higher than equivalent area of concrete is more than equivalent area of steel. So therefore, we can say neutral axis, if the area of concrete is higher, equivalent area, in that case, we can say now the neutral axis lies in concrete only, right? This is about position of neutral axis. Next is about position of neutral axis. So if I'm looking into the position of neutral axis, we can compare compressive forces with tensile forces, and from that we can position of neutral axis, just same as your RCC. So it is 0.87 into Fy into area of steel, which is 9227, divided by 0.36 into 30, that is grade of concrete, multiplied by 2500. So from here we will get 74.3 mm, and which is from top. So next we can calculate. So the position of neutral axis is, it is 74.3 mm from top. Moment of resistance we can calculate. Moment of resistance we can calculate, it is, so point, if I'm looking into the steel, from steel side, it is 0.87 into ES, which is 9227, multiplied by Fy and multiplied by distance from neutral axis of steel to CG, which is 350. From where we are getting 350, it is 450 divided by 2 plus it is 225 plus 125. Depth of concrete minus 0.42 XU, right? And the XU is 74.3. Therefore, from here we will get a value around 640 kilonewton into meter, and which is more than design moment in composite stage, which was we wrote it on stage 6 in at initial point. It is 463.575 kilonewton into meter. Therefore, we can say it is okay. It is okay in composite, moment of resistance in composite, as well as in construction stage. It is okay. Next is design of shear connector. So, since the position of neutral axis in concrete, therefore, we can calculate it from is in concrete. Therefore, total load carried by connector, we can calculate it by 0.36 FCK B effective into XU, 0.36 FCK B effective into XU, and here we can say it is 0.36 into FCK is 30, and B effective is 2500, and XU is 74.3. So from here we can say it is around 2006.1 kilonewton. So next is, this is about the load which must governed by connector, right? So here if you are looking into this particular table, which is taken from IS 11384, this is a table 1 which gives the value for design strength of shear connector. So from here you can take any size of connector. From here you can take any size of connect. Just a second, it is little bit slow. Yes, it is visible, hopefully. So these are the different grade of concrete for grade M20, for M30, because as we know, if we are increasing the grade of concrete, the resistance must increase. So therefore, based on that, the strength capacity of connector also increase. So therefore, if you are looking for 25 mm connected headed shear connector diameter having height 100 mm, for M20 grade the strength design strength is 86, for M30 it is 101, and for M40 it is 113. Similarly, for 22 mm with different dia, it has different. So in this particular case, I am taking 20 mm headed stud with 75 mm height, and the grade of concrete given in question is M30. Therefore, the design strength of connector is 58. And usually, if you know the ultimate strength of concrete, usually in plastic design, we are taking 0.8 times of ultimate strength, which is usually we are defining strength of double strength of connector is by D. So it is, if you know the actual strength, in that case you can take it as 0.8 of D also. And don't confuse with this D. This is diameter, about diameter. So usually if you are looking into the particular geometry of connector, usually we are providing head diameter is 1.5 times of shank diameter, and in any case the spacing between two connectors should be more than, for different criteria it may vary from 3D to 6D. It is also given in IS 11384 also. So as we know, for we are selecting 20 mm diameter headed stud with 75 mm height. So that the design strength is equals to 58 kilonewton into meter. Therefore, if I'm looking into the total number of connector, so the total number of connector is equals to as we know, the total force is 2006.1 kilonewton. If I'm dividing it by 58, I will get the number of connector, which is approximately 34.58. So I can say I will provide 35 number of connectors. So next is about spacing. So there is one important point whenever we are looking into the connectors. As we know, whenever we are talking about shear, it goes like suppose this. So we are providing 35 number of connector in half of the span. If the total span length is 10 meter, then we will provide this 35 number of connector in this L by 2 span, or we can say 5-meter span only. So the total connector requirement is 70, not 35. It is total number of connectors is 35 into 2, which is 70 numbers. So if I'm looking into the spacing, I can say it is length, which is, as I told you, we are considering it in half span divided by 35, which is the number of connector. So from here I will get spacing. So I'm getting 142.86 mm, or I can say it is 140 mm also we can provide at 140 mm. We can provide it at 140 mm. So this is about one row of connector like this. If the span length is, this is about one row of connector. If, as we know, in our case it is the width of this is 150, and as I told you, the minimum spacing requirement between the stud is 3 to 5D. So if I'm looking into the 3 to 5D and the corner it is 1.5D. So if I'm the diameter of connector is, so if I'm removing 30 from here and 30 from here, I will get 90 over here. So it is almost 4.5 times of D, right? If D is 20, so it is 4.5 times. So I can provide two rows of connectors also, like this also. So in that case, this spacing goes 140 multiplied by 2, I can say it is 280 mm. So if you want to provide it in two lines inline pattern, that is known as inline pattern. And if you think that the spacing is very low, in that case you can provide it in a staggered pattern also. So this is one line of stud with spacing of 280 mm, and this is instead of, just a second, it will take only 2 more minutes. Yes, and you can provide it in staggered patterns also. If you wants to provide it in two rows, this is staggered pattern, and the spacing is again 280 mm. So that you will not get any kind of conjunction. So next is about serviceability. Serviceability, we will check it for on deflection as well as stresses, and we will take load factor as 1. Initially we have considered 1.5. Now we have to calculate by 1 load factor, and based on that, the modular ratio for live load and dead load, it is given here. And if you are going for serviceability, for live load it is 15, and for dead load it is 30. Why it is more for dead load? Because in dead load the long term effect are also considered. Because of that it is 30. And this is about deflection. As we know, for simply supported it is, and if the UDL is acting over it, in that case it is 5 upon 384 WL4 upon EI. So we can tell I for steel it is given, because in initially if the total deflection, if the deflection is governed by steel in dead load, in that case we can calculate it by moment of inertia of steel. If we are looking into the live load, in that case we can go for composite. So in that case we have to calculate moment of inertia of composite section also. So based on that we can calculate deflection and stresses, and at the end we can calculate shear, and based on that we can provide reinforcement also. And these are the, as initially I have explained some part. So if the position of neutral axis is in concrete also, if it is at the interface level, if it is at the wave of the steel, in that case, how we can calculate moment capacity and position of neutral axis, these are given. So that is all from my side. If there is any question.
Thank you, Dr. Pankaj, for this wonderful session.
So
We have
once again, sorry from my side because it was too lengthy and we cannot complete one problem in this uh, 2 hour duration. That is an issue because in composite we have lots of aspects to consider.
that is understandable. We had a tall order in front of us in a very limited time. But I hope all who have attended could benefit a little bit from the design that you have explained very efficiently. I would now request Dr. Pankaj, would you please check the questions in the text boxes and
Just a
answer
second.
as many of them as possible?
Just a second. I'm just looking.
So, Neha madam asks,
Neha Rajput ma'am, which construction are prefers the composite structures? Uh, sorry ma'am, I'm not getting in which aspect you wants to know.
which construction area basically?
In mostly in infrastructure we can say where large span is required.
And
Neha ma'am, am I audible?
Miss Neha, you can ask any other questions that you have.
And we have which code software and book are preferred for this structure. As I told you, it is IS 11384. I think this question was bit earlier. It was around 11 o'clock. After that, we start the design, and I repeated constantly so many times. It is as per Indian code. It is IS 11384, and as we have Eurocode also, Eurocode 4 Part 1 and Part 2, and similar to BS 5950 also. And I think, could we get this example of? Yes, ma'am, you can. And it has already been shared. Not visualization. Please check.
That is not
Uh, some of the firm that is personal kind of. How is the connection between foundation and column? Any virtual representation available? Yes, of course. So many. So that is all, I think.
okay. Okay, thank you, Dr.
Um,
Pankaj. I would now like to open the podium for any questions that the members from the audience have. Please ask your questions. You can just unmute yourself and ask your questions. There is no need for typing it anymore. Okay, in that case, I suppose everybody has probably understood what Dr. Pankaj has been telling us. With this, uh, we will we are moving towards the conclusion of the session, and in the concluding remarks, I can you please give some insights about the fatigue and life calculation for composite beams?
So usually for fatigue, if you are looking into the characteristic strength also, in simple static design, we are considering it around at 5% probability, and we are considering different. But for fatigue, again, there is again characteristic strength also. All of the parameters are different. So, and again, we are taking almost same load factors also. And again, in fatigue, it is about concentration of, sorry, The magnitude of load, it also depends upon magnitude of load and number of repetition.
Okay. I hope that answers.
सर डायनेमिक स्ट्रक्चर के लिए ओके है क्या?
And dynamic structure, sorry, I didn't get.
Can you please elaborate on what do you mean by dynamic structure, sir? Manish sir. A structure that is repeatedly subjected to dynamic loads, or what is exactly the point that you are trying to make? In case of structures which are subjected to dynamic loads, probably Dr. Pankaj, if you would like to answer.
Yeah, if we are as I told you, there is lots of stress concentration point available, because whenever we are inserting stud in concrete, in static loading also there must be some stress concentration. So after certain time period, there is in bearing portion as well as in shearing, there must be some crushing zone at bearing portion at stud also available, as well as in shearing portion also there must be some crushing. Because of that, there is a cavity form at in surrounding concrete of the connector, and because of that they lose interaction or between concrete and headed stud. In case of composite, if you're looking into the composite, so the researchers are right now working on this particular area, and that is why they introduce adhesive bonding, because in adhesive bonding there is no issue of crushing. If you will reach, and if you don't reach up to the ultimate stress kind of thing, in that case it is perfectly fine, it is working perfectly fine, and in lots of composite they have tested also. But in case of mechanical connector, whether you are putting them in impact also, they are these are the disadvantages of composite connections, or we can say composite constructions.
There is one more question from Neha ma'am. Please, Dr. Pankaj, she asks, what would be the L/D ratio for composite beams, one way and two way slabs?
So it is like for beam, if we are looking into the beam for simply supported, it is in between 15 to 18. Usually they are considering, and for continuous, they are considering in between 18 to 22, 25 kind of.
Okay, I hope that answers the question of Neha ma'am. I would now like to request. Yes, Vimal sir. Hello. How are you?
Hello, sir. I'm good. I'm Vimal Kumar, working as a faculty at NIT Hamirpur. First of all, I congratulate the organizing committee, Dr. Shatar and his team for arranging this. Good afternoon. For arranging this lecture, and also thank Dr. Pankaj Kumar for presenting this topic. This is really very informative, and definitely help the students to gain some knowledge. I have one small doubt.
Yes.
At one side, Dr. Pankaj have shown some about connections, where he discussed about whether the shear strength is more than the strength of the concrete, or
Yes.
it is less than that. Okay, at one side slide.
Yes.
And also about the strength of the steel.
Yes.
Where he discussed about the partial and full connection.
Yes.
Okay. And in the next slide, he discussed three curves: one for semi-rigid and rigid, and one more curve is there.
Sir, that one first slide was degree of connection, and second one was degree of interaction rates.
Okay. So whether these are for the same full connection, partial, and no connection, these three curves are related to them, or it is different?
These are different, sir. Actually, in degree of interaction, we are
semi-rigid is different than the partial.
Yes, sir.
Yes, please.
They are more or less they are correlated to each other, but they are different, because in one case, like in degree of interaction, we are considering stiffness of connection at interface level only. But in second case, likewise in degree of connection, we are talking only about strength only. We are defining only strength. Whether the connector have more strength, concrete have more strength, or steel have more strength.
Okay. And my next question is that the strength is which strength? Is it shear strength or something else?
Shear strength, sir. Shear strength. For connector, it is
compressive, which strength? Because usually the steel has okay. And the strength for concrete is also shear.
No. For concrete and steel, it is
In the same slide.
So it was, I think, it was written like P. So it is about bending.
P concrete is greater than. I'm not audible, sir. Please. Hello.
Dr. Pankaj.
Yes, sir.
I think Dr. Vimal is asking about the notations and the stress strain behavior. In fact, the stress pattern, the stress distribution in terms of when in case of connections with where we are talking about degree of connection. So if you want, I can show the slide and you can describe it probably once more.
Just a second. Yes, sir. In degree of connection, you are confused with both the term in shear also as well as in concrete and steel also. We are writing same notation like P, right, sir?
Yes. Yes, Dr. Pankaj.
Yes. So, is there any confusion about the strength? That is not about shear strength of concrete or steel. It is about capacity of concrete and steel available at that cross section. We are considering shear strength only for headed stud connector. So, although notation is written over here almost same for all three of them is P, but it is different.
Okay, the next one is the slide number 22. 21 or 22.
Yes, sir.
This 22.
Yes. Yes, sir.
This is yes. This. Okay.
And
so the rigid. Okay, that is, it is different.
Yes, load slip curve.
Could you please give your opinion on this?
Dr. Pankaj, it's just he's probably asking for an illustration on this curve. Why different lines for different curves?
So this is if you are looking into the connection, you are talking about connection characterization.
Yes, he is.
Yes, sir. The first line, there is a load, applied load versus relative slip curve. There is a vertical line which shows ideal rigid connection. It means there is no slip, or we can say at the level of interface, there is infinite stiffness available. Second one is about rigid connection with brittleness. So likewise, if you are looking into the rigid, flexible and semi-rigid kind of connection, as per IS classification, they are defining with 6 mm slip. Whether if the slip is more than 6 mm, they are defining them in flexible kind of connection, and if the slip is lesser than 6 mm, in that case they are defining by rigid connection. That is about type of connection, which is flexible, rigid, semi-rigid, and ideal rigid kind of connection. And they are considering in between them somewhere rigid. There is no particular classification for semi-rigid kind of semi-rigid kind of connection. And second one is about with brittleness and with ductility and without brittleness. That is about the ductility of the curve. As we know, the ductility is a total deformation to the yield deformation. So therefore, this is only a representation only. If after yield there is significant ductility is available, that is showing significant ductility, and if there is no ductility available, in that case it shows brittleness only. That is about the ductility ratio.
Okay. Okay, Dr. Pankaj, thank you.
Okay, thank you, sir.
Dr.
Hello.
Pankaj, I have a question. On the same slide, 22. Could
Yes.
you please elaborate on the flexible collection? Like, what are the examples of a flexible collection?
Likewise, headed stud connector, also if they are placed at distance like 10D from each other, and they are a flexible connection because they are showing significant slip at the level of interface. And as per IES, if the slip is more than 6 mm, usually we are getting more than 6 mm. In case of if the beam span is more than 4 meter and 5 meter, in some of the cases there is lots of practical example as well as researcher problems are also available, in which they are showing slip around 10 to 12, 12, 15, 22 mm. So that is usually known as flexible connection.
Okay, thank you.
सर हेलो
Yes, sir.
सर मेरा डाउट ये है कि सर जो हमने कनेक्टर लिया है तो
Yes.
अगर कनेक्टर को ना लेके हम फ्लेंज को ही कंक्रीट के सेक्शन में
Sir, in that case, agar if you are inserting direct flange inside the concrete, na, so there is, as we know, there is no like in if you are looking into the plain steel and core steel also, there is no bonding between concrete and steel. So if the member is subjected under flexure, in that case, they must be debond and the surface must be delaminated. Because as you know the bottom side, either if you are completely inserting inside, that is the ideal case in case of columns, but it is not ideal case for beam.
ओके सर मतलब बीम के लिए अच्छा रहेगा और स्लैब के लिए
नहीं
कॉलम
नहीं फॉर कॉलम के लिए बेटर है, फॉर बीम इट इज नॉट गुड.
ओके सर थैंक यू सर थैंक यू
Dr. Pankaj, there is one more question from Kishore sir. He asked, we provide a beam in strip seal of expansion joint in bridges. Is this an example of composite beam?
We provide a beam strip seal. No, sir. Hopefully not.
Hopefully.
Because usually all of the, if you are using any kind of seal, these are polyurethane kind of adhesives. So they are showing they are not showing any kind of strength. Therefore, there is no composite action kind of. There is no shear strength available. So there is no composite action between. And if there is no composite action, that is not comes under composite beam.
Okay. I hope this answers Kishore sir's question. Uh, in that case, I would like to thank Dr. Pankaj once again for so patiently answering all the questions asked during the session and taking us through this wonderful journey of uh, design of composite beams. In conclusion, I would like to request all the participants to please fill the feedback form that will help us improve of our content as well as our presentation in the future. And If you have any other questions, queries, or suggestions, you are free to write to me at the email ID that you have already got with all of you. Thank you very much, and let us once again thank Dr. Pankaj for his wonderful presentation. Thank you, Dr. Saab. Thank you.
Thank you, sir.
And
Thank you.
I
Thank you,
once again
everyone.
thank all the participants for being here, for being a part of this workshop, hands-on design. Thank you. Thank you all.